The complex number z equals 1 minus 4i, where I squared is minus 1, of course. Plot z and minus 2z on the argand diagram. The real part of z is plus 1, which is here. The imaginary part is minus 4, which is here. So the complex number 1 minus 4i is this point here. What about minus 2z? Well, that's just minus 2 times 1 minus 4i. Minus 2 by 1 is minus 2. Minus 2 by minus 4i is plus 8i. So the real part of minus 2z is minus 2. The imaginary part is plus 8. So the complex number minus 2 plus 8i can be represented by this point on the argand diagram. So this point is also called minus 2z. Show that 2 times the modulus of z equals the modulus of minus 2 times z. Let's look at the modulus of z. We need to get the modulus of z before we can get 2 times the modulus of z. The modulus of z is the distance of 1 minus 4i to the origin. It's this distance here. Now, this distance is essentially worked out from Pythagoras' theorem. We have this right angle triangle. This horizontal distance here is 1. The vertical distance here is 4. So the two short sides of this right angle triangle are 1 and 4. So the modulus is the length of the hypotenuse, which is the square root of the sum of the squares of the two short sides. So that's square root of 1 plus 16, or the square root of 17. So basically, when you get the modulus of a complex number, you square the real part, so that's 1 squared. You square the imaginary part, that's minus 4 squared, which is the same as plus 4 squared actually. You then add these values and take the square root. It's just an application of Pythagoras. So the distance of 1 minus 4i to the origin, this distance here, is the square root of 17. Now, the left-hand side of this equation is 2 times the mod of z. That's 2 times the square root of 17. Now let's look at the right-hand side. We want to get the mod of minus 2 times z. Well, we've worked out minus 2 times z already. It's minus 2 plus 8i. So we want the mod of minus 2 plus 8i. Well, what do? We get the square root of the real part squared plus the imaginary part squared. Minus 2 squared is plus 4. 8 squared is 64. 4 plus 64 is 68. Now we want to show that 2 times the mod of z, which is 2 root 17, equals the mod of minus 2 times z. So how could we do that? Well, you could just go to your calculator and just work this out. And you could also just work this out, but I'll do this a bit differently. I will look at the square root of 68 and factorize 68. 68 can actually be written as 4 times 17. And we can take the square root sign over each factor. Square root of 4 is 2. So it is indeed true that the square root of 68 is 2 root 17. So when you're looking for factors of 68, you want 17 to be hopefully one of them. So you divide 68 by 17 and you get 4, and then you can break this down. So you can show that root 68 equals 2 root 17. So now you can see that 2 mod z is indeed equal to the mod of minus 2 times z. It's true. What does part B tell you about the points you plotted in part A? Well, we got the modulus of minus 2z. That's the distance of minus 2z to the origin. Remember, it was just an application of Pythagoras. This distance is 8, this distance is 2. Root 8 squared plus 2 squared is root 68. So, what part B tells us is that 2 times mod z, in other words, 2 times the distance of 1 minus 4i to the origin, is equal to the distance of minus 2z to the origin. The modulus of minus 2z is just the distance of minus 2z to the origin. So if we put one tick here to represent this distance, which is the mod of z, then this distance here is going to be 2 ticks, if you like, where this time 2 ticks does indeed mean twice this distance. So in words then we could say, I'll write it over here, distance of the complex number minus 2z to the origin is twice the distance of the complex number z to the origin. As an aside, let's have another look at the modulus of minus 2 times z. It's a fact that when you get the modulus of a quantity, you can get the modulus of each part of the product. So there are two terms multiplied in here. We have minus 2 multiplied by z. So we can get the modulus of minus 2 times the modulus of z. You can do that if you have the modulus of a product is the product of the moduli. The modulus of minus 2 is the distance of minus 2 to the origin. This distance here, which is just plus 2. Modulus of minus 2 is plus 2. We could call it the absolute value of minus 2. When we get the modulus of a real number, we sometimes say we're getting the absolute value. We just make that real number positive. So this is true in general. We can, so if we knew this fact, we wouldn't have to show this. So it's true for any complex number z, not just the particular complex number in this question. Let k be a real number such that the modulus of z plus k equals 5. Find the two possible values of k. Let's just look at z plus k. We have z here, it's 1 minus 4i. We add on k. K is a real number, it doesn't involve I. So we can bring that k next to the 1. And we can now write out our complex number like this. The real part is made up of terms that do not involve I. So I can bracket the real part. The real part is actually made up of two terms here. I could write RE underneath this for the real part. The imaginary part is the coefficient of I, which is minus 4. So z plus k is the complex number 1 plus k minus 4i. How do we get the modulus of a complex number again? We just get the square root of the real part squared plus the imaginary part squared. I obviously can't draw a picture here because we don't know what k is. So the real part is 1 plus k, we square it, and then we add on the imaginary part, minus 4, and square it. You don't have to put the minus sign in because when you square a negative, it's positive anyway. We're given that the modulus of z plus k is equal to 5. So we have an equation here with the unknown k. So we can solve this equation to find k. Now, to solve this equation, what we should do is square both sides to get rid of this square root sign. So I'll continue writing up here. If I square the left hand side, we get 1 plus k squared plus minus 4 squared. Well, I'll just write down plus 16 for that. But then we must square the right hand side. 5 squared is 25. So now how do we find k? Well, we isolate 1 plus k squared. And we bring the 16 over. 25 minus 16 is 9. How do we solve this for k? Now a lot of people will go and square this out, then bring the 9 over and you'll have 0 on the right hand side, quadratic equation, solve it, all the usual. But that's a waste of time, because we have something squared equal to 9. If 1 plus k squared is 9, then 1 plus k itself must be the square root of 9. The square root of 9 is either plus 3 or minus 3. So if 1 plus k is plus 3, then plus 3 squared is 9. If 1 plus k is minus 3, then minus 3 squared is also 9. So we have reduced this quadratic equation to two linear equations. One of the linear equations is 1 plus k equals plus 3. The other linear equation is 1 plus k equals minus 3, because the square root of 9 has two possible answers, plus 3 or minus 3. So we solve each of these linear equations in turn. So k for this one is equal to 3 minus 1, which is 2. And for this equation, k is equal to minus 3 minus 1, which is minus 4. So these are the two values of k. We can very quickly check these. Now, as an aside, I will just show a mental check. If we plug 2 in for k here, we have 2 plus 1 is 3. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. The square root of 25 is 5. It checks out. If we plug minus 4 in for k, we get 1 plus minus 4, or 1 minus 4, which is minus 3. Minus 3 squared is plus 9. 9 plus 16 is 25. The square root of 25 is 5. So both of these check out